Alright, so continuing on the topic of efficiency in the context of embedded system design, there is one topic that we need to that is well worth understanding in a little bit of detail, and that's called direct memory access. Okay. So in order to understand why direct memory access is required in the first place, we are just going to recap what a typical CPU system looks like, right? So what I have over here is there is a CPU which is what we call the primary master on the bus, right? And you may recall that a bus is basically a set of wires that connects the the CPU with the different parts of the system. It could be the memory on the system, it could be an IO device, it could be some other kind of peripheral, right? And the reason why the CPU is called the master is that the CPU basically puts out addresses on the bus. If the address corresponds to something in memory, then the memory is supposed to respond to it, which makes the memory basically a slave as far as this bus structure is concerned, right? It responds to a request which is coming from the primary master. Now instead, if I wanted, let's say, a UART, I would actually read or write from a particular address, right? And that would either tell me that there is data sitting in the UART, or it would allow me to write data out to the UART. Once again, the CPU acts as the master. It could be some other peripheral, it could be a display, it could be a printer, it could be some other thing where basically once again the CPU decides when to transfer data into or out of the peripheral. Now all this is fine, right, and this is typically how computer systems work, except for the fact that the CPU is involved in every single one of these data transfers, right. Examples are plenty, right. A UART receives data. If I want to copy that data into a buffer in the memory, the CPU has to do it. When I have Wi-Fi and I need to transmit, let's say, a block of data, or I am downloading a page from the internet, the CPU has to either copy data into the transmit buffer or wait for the data that has come into a receive buffer, right, receive as and when each and every byte comes in, it has to basically pull it in and put it somewhere into memory, right. And the video display, typically we want to have display screens that are refreshing around 60 times per second, right? And if a CPU had to basically go and copy the pixel values for each and every one of the pixels 60 times per second on a screen, the CPU would not have time to do anything else. Now interestingly, in the early days of computers, this pretty much was the way to go, right? I mean, you didn't really have a choice. Your CPU had to be able to handle all this kind of work. But very rapidly, and in fact in the early days of computers itself, people realized that this was just infeasible. You can't really sort of scale a system this way. It needs to be doing useful work. It needs to actually be performing computations, right? In all of these cases, the CPU is only transferring data. The entire ALU, the arithmetic and logic unit, which is sort of the core functionality of the CPU, is not even being used. The alternative is to bring in a secondary master on the bus, right. So this DMA, the direct memory access controller, acts as a secondary master on the bus. In what sense? In the sense that it can now start generating addresses on the address bus, right. So it can, for example, read data from memory, and if what you wanted was to take a chunk of data sitting in memory and to write it out into a Wi-Fi transmitter, right, the DMA would basically be able to take the data from here, generate the addresses to read, and also perform the write transaction in order to write it out into the IO device. Let's say that you wanted to update something on a screen. The DMA could be told to basically take data from a certain part of memory, which maybe we would call the frame buffer, and just copy that data out into the video screen, the peripheral, right. During all this time, the CPU is not involved, meaning that it does not even need to get onto the bus, okay. Now that's fine, except what if the CPU does want to get onto the bus, right? You notice that we now have two masters on this bus, and there is automatically that raises the question, who gets to talk at any given point in time, because there is only one physical shared bus. Now over there, a concept of something called arbitration comes in, which means that this bus requires something else called an arbiter. There is another piece of circuitry that receives requests for using the bus, one from the CPU, one from the DMA. It decides who has higher priority and gives access to that particular master so that it can make use of the bus. Okay. So, effectively a DMA is a memory only bus master. Right? What does it do? It can generate addresses as well as the control signals required to read from an address or write to an address. In other words, any memory related transaction can be initiated by the DMA controller. The good thing is it basically allows you maximum utilization of resources. There is no computation involved, only data transfer, right? And you can even have more complicated sort of patterns of data transfer. You can do something called burst transactions that allow you to copy large chunks of data from one region of memory to another region of memory, or to a peripheral, or to an IO device, or vice versa, right? All of this is enabled by what's called direct memory access, or DMA. Now, the DMA device by itself, interestingly, doesn't know what to do because it does not perform computations, it does not have the ability to fetch and execute instructions on its own, which means that apart from being the secondary master on the bus, the DMA itself also has a slave interface in general, which means that the CPU can connect using some kind of configuration address to the DMA device and set some register values that basically say, okay, this is a start address of where I want you to copy data from, this is the length of the transfer, the number of bytes that I want you to transfer, and this is the destination address, the first address into which I want the data to go. And then there will be one more sort of a control register where it actually, the CPU writes a value saying, okay, now start the transfer, right? And once that is done, the DMA can take over generating the addresses for actually transferring the data, right? And the CPU in general can do other work in the meantime. Now, that's a bit of a loaded statement, because what if the CPU also wants to access memory at the same time, right? If that is the case, then strictly speaking, this whole idea of having a DMA sort of becomes problematic, right? What do you mean by saying that the DMA can access the bus? Doesn't the CPU want to also access the bus at the same time, right? Now, in order to understand that, we also need to sort of very briefly talk about the idea of a cache, right? I mentioned the word cache previously, but just in case you are not completely familiar with what the idea of a cache is, a CPU does processing. It has an arithmetic and logic unit and has the ability to execute instructions. But what it does is it actually loads and stores data from and to the main memory, which is the place where a large amount of data can be stored, and the actual working material, working data corresponding to your program is stored in the main memory. Now, the problem is typically CPUs have been improving over the years and are extremely fast, right? And as you are probably aware, the CPU clock periods that are used for CPUs are typically hundreds of megahertz even for many embedded systems, and in the gigahertz range for regular desktop or laptop kind of CPUs. Main memory, on the other hand, typically has significantly higher latencies. They might have high throughput, high speeds, right? But in order to access, let's say, just 1 byte of data from main memory, it actually takes a significant amount of time, right? After that, reading a chunk of data from main memory might actually end up being fairly fast. So what is usually done in pretty much all computing systems is that another block called a cache memory is introduced. What cache memory does is it sits between the CPU and the main memory and says if the CPU wants to access something from main memory, it first checks whether the data is present in the cache. If it is, the data will just come back from the cache itself. If the data is not present in the cache, then the cache will send out a further request to main memory, get the data back in here, and that is then sent forward to the CPU. Of course, this is almost transparent, so it's not like it takes time it takes a lot of extra time at least in order to sort of store it into the cache and then send it across, right? If it's not present, it's pretty much the same latency as actually reading from main memory, except that it goes through the cache, right? Now, what's the advantage? The cache is much smaller and can be designed in such a way that it can have latencies that are significantly less, tens of cycles, possibly even almost at the same speed as what the CPU can work. Now, how does that help? it means that, for example, if the CPU is repeatedly performing operations where it needs to get some data from memory, that data, it's possible that it just fits within the cache. More importantly, what about the instructions corresponding to the CPU? They are also coming typically from the main memory, but let's say that the program that I am running has a loop. Then what ends up happening with that loop is there are a small set of instructions that are just getting repeatedly executed over and over again. Each and every time, rather than going out to main memory and fetching instructions from there, what I would like to do is the first time around those instructions come into the cache, and from there onwards I just basically go back and forth between the CPU and the cache. Right? So this is a very common practice. The use of caches has been validated in terms of performance multiple fold over the years, right? They are an essential part of pretty much any kind of computer architecture at this point, to the point where even relatively low cost embedded systems very often have a little bit of cache memory at least. It's probably on the range of a few kilobytes rather than the megabytes or gigabytes that main memory is, but even that can make a significant difference to performance. Now, with this in mind, with the fact that either your instructions could be sitting in cache or possibly even some of the data that you need is sitting in the cache, right? What that means is the CPU very often may not actually need to hit the bus and go out to main memory, right? And what that in particular means is that I could have a scenario where, as far as the memory is concerned, the CPU reads some data. From there onwards, the CPU is basically talking only to cache, right, and performing computations. During that time, the DMA can basically take over and transfer some data from one place to another. After that, the CPU eventually comes back and starts reading from main memory again. Now, is this guaranteed? By no means, right? But it is a common enough pattern that in practice you actually get fairly good performance overall from something like this. Now, there are variants of DMA. One of them is what's called cycle stealing DMA. And what happens in cycle stealing DMA is the CPU configures the DMA to do a data transfer. It basically says, transfer some X amount of data from one address to another, right? But the CPU is also continuing to do other work, and it in fact needs to access the main memory on a fairly regular basis. It has to go about, loading data from some memory locations into registers, performing computations, putting the data back, and so on. So what happens here is that the DMA module takes care of constantly requesting for bus access, right? And as I said, there is a specific piece of circuitry within the system called an arbiter, which basically gets these request signals both from the CPU as well as from the DMA module. The CPU is generally given very high priority. So if the CPU requires access to the bus, usually priority goes to the CPU and the CPU gets access to the bus. But the CPU is not always loading or storing data. If it was, then probably the DMA was not necessary, or this is just a badly designed system. So it is very likely that there will be gaps in between the CPU actually requesting access to the bus. Whenever there is a gap, the DMA gets granted control of the bus and it performs a few transfers, right? Maybe a few bytes are transferred and then it gives the control back. The CPU can then go on. If the CPU by any chance doesn't actually use the bus, the DMA again kicks in because it will probably put in a request immediately after it has first transferred a set of data. What that means is that the DMA is continuously managing to transfer some data over time. It doesn't wait for a long chunk of time during which a large amount of data can be transferred, right? It basically sees whenever it finds a gap in the CPU usage of the bus, it transfers some data, which means that from a macro level, when I look at it on the millisecond or tens of millisecond time scale, it looks as though the DMA has been transferring data all along while the CPU was also active, right? Now this allows some really interesting real-time use cases, especially for things like audio, where the sampling rate is actually not terribly high. It's on the order of tens of kilohertz, right? But you need to have real time, because if I miss the deadline within which data has to be actually copied into the either the transmit buffer or the processing buffer or the filter or whatever it is that I have, I will actually suffer a loss in quality, right? But by having cycle stealing DMA like this, I can ensure that the DMA looks for any gap in the CPU's usage of the bus and just transfers the data during that time, and overall can do a very good job of meeting the real-time requirements that I have. Similar things can be done with network or with disk read and write and so on, right? And this mode of operation of DMA is very useful in practice. Now, finally, we talked about interrupts earlier. Interrupts and DMA are related. Now, the first thing that should not be done is that you should generally not be running a DMA inside an ISR, right? Because this goes against the entire idea of an ISR being fast, whereas DMA is usually used for bulk transfer of data, which presumably would take a long time. On the other hand, we can use it very nicely in the opposite way, which is that the DMA can be initiated by the CPU, and once it's done, it generates an interrupt. This is sort of the ideal use case, right? The DMA has been given a long-running background task. We don't know how long it's going to take because it might have to steal cycles from the CPU, but as and when it's completed, it wakes up the CPU, and the CPU at that point can then decide what to do. It basically wakes up on the DMA interrupt. It could either be in deep sleep or low power, or it could be doing some other work, right? For the audio processing, for example, let's say I have one chunk of data of, let's say, a few tens of samples, right? And I ask the DMA to transfer it, right? Or rather, I accumulate, let's say, several hundreds of samples and ask the DMA to transfer it into another location, during which time the CPU starts working again. As and when the DMA completes, it once again wakes up the CPU. The CPU can go and check, okay, now there are another 100 samples sitting in the bus, initiate the next transfer, right? So, interrupts and DMA play very well together. You can combine them for very efficient use of your hardware. So, these are two sort of key components that can be used in order to improve the way that your entire system can be used.